everyone, welcome back. Today I want to explain a small but very important idea that often gets skipped when we talk about solving systems of differential or difference equations, which is why do we take the determinant of a minus lambda I identity and set it equals to 0. You've seen this step many times when finding eigenvalues, but the reason behind it is actually very simple and quite beautiful. So let's talk about the intuition. Suppose you have a matrix A and a column vector B x, and you have a column vector B where A is a m into n matrix. Therefore, x is going to be a n into 1 column vector, and therefore b is going to be a m into 1 column vector. So x is basically a vector in the n dimension, and b is a vector in the m dimension. Okay, we know that a solution will exist when the inverse of the matrix exists, right? So we know that if we take the inverse of the matrix and we multiply it by both sides, we're going to get a unique answer for x, which is A inverse of B. So therefore, whenever the inverse of a matrix exists, we will get a unique solution. Okay, so suppose what is the inverse, by the way? The inverse of any matrix is basically the transpose of the cofactor matrix, and you also divide it by the determinant of that matrix, which means that if you want the inverse to exist, the denominator, which is the determinant, cannot be equals to a 0. So therefore, whenever the determinant is not equals to 0, we have a situation where the inverse will exist, and therefore a unique solution will exist. Okay, so a solution will exist. Relating this to the characteristic equation when we were doing coupled difference and differential equations, remember we know what is the definition of an eigenvalue and eigenvector? It is that an eigenvector has to satisfy this equation where v is known as the eigenvector and lambda is known as the corresponding eigenvalue. So this system is written as lambda identity v is equals to a 0. You can think of this as a system where the value of the constant b is equals to 0. So if I had written b is equals to 0, the system would have become ax is equals to a 0. And if the determinant of this was not equals to 0, it would have implied that the inverse existed. And if the inverse existed, we would have found the solution, which was when you multiply the inverse into 0 by 0 in a column vector which has all zeros in it, you simply get the trivial solution. So you get an x which is equals to a 0. So you get a column vector which has all zeros in it. It's called the trivial solution. Okay, so remember that we actually need a vector which is non-zero vector. So suppose I said the determinant of this matrix was not equals to 0. This would have then implied that the inverse of this matrix would exist, and therefore I could have just got a V which would have been the inverse of whatever this matrix was, and I would have multiplied it by the column vector which had all zeros in it, and I would have gotten a eigenvector which had all zeros in its rows. So this is the problem here. I don't want, this would give, for instance, if suppose V was a two-dimensional eigenvector, it would have looked like this. This is not what we want. We need a eigenvector which is non-zero. Okay, so therefore the only way we can get a non-zero, so I want a eigenvector which is not equals to 0. So this exists if and only if the determinant of this is a 0. And this basically, when you solve this equation, this gives you the characteristic equation which gives you the value of the values. Yeah, so it gives you, when you solve this, you get the value of lambda 1, lambda 2, and so on, however long your system was. So that brings about an end. So the next time you see the determinant of A minus lambda I is equals to 0, remember, we're not doing some magic trick. We're simply making sure that the system has a meaningful solution, one that actually leads to a actual solution in our model. So anyhow, thank you for watching. If this makes things clear, feel free to like and share, or leave a comment telling me what concept you want me to explain next. See you in the next video. Take care.